Hi, welcome back. In this video, we're going to be talking about the extreme value theorem. The extreme value theorem is the justification for our expectation that a function continuous on an interval would have a maximum and a minimum. If you've solved a bunch of optimization problems in your calculus classes, then implicitly you are counting on the extreme value theorem to be true. It's a theorem that predicts if you have a continuous function, then it will have a maximum and a minimum. Now, the statement that we have here is only for a maximum, but the same thing applies for a minimum. So let's have a look at the theorem. The theorem requires a function f, which is defined on a closed interval a, b, and the function must be continuous on that interval. And then it predicts that the function will have a maximum value on that interval. What is a maximum value? A maximum value is a single value, although it could have multiple, is a value x naught somewhere in the interval a, b, so that f of x naught is bigger than or equal to f of x for any other value. So in this picture, the function f might be defined on a, b, and then I'm sort of suggesting we don't really know what happens up here. Something weird happens up here. That's why I've got it dotted. But somewhere in here, there will be a value x naught. And the value of the function at x naught will exceed or equal any other value of the function on this interval. So that will be the extreme value of the function. So we call this the extreme value theorem. In this phrasing, we're only stating this for the maximum, so we could call this the maximum value theorem in this phrasing. There's a similar statement for the minimum as well. Before we get to the proof of the extreme value theorem, I want to caution you. It depends very delicately on these hypotheses. It is not correct to just say, oh, I have a function, so it must have a maximum value. And I want to illustrate some counterexamples to show you that all of these hypotheses are important. First of all, that the interval is closed. The AB is a closed interval. If we look at an open interval, a function might not have a maximum value at all. So here, let's do f of x equals 1 over x on the open interval from 0 to 1. So here, this function on this open interval, so we have a hole here, and then this part of the graph is removed. And now this function is not defined at 0, but it is defined on the open interval from 0 to 1. And what does it do? It just goes up to infinity here. So here we have no maximum value. And the extreme value theorem, or the conclusion rather of the extreme value theorem for this function is false. Why is it false? Because the interval was broken. The interval was an open interval. The extreme value theorem applies only to closed intervals. So let's look at another example. So this illustrates that on an open interval, this theorem would be false. Well, rather, the conclusion of this theorem would not hold because the hypothesis doesn't. Next, let's illustrate that f really needs to be continuous to have this expectation, then it'll have a maximum value. Even if the function is defined on a closed interval, say 1 to 5, if we have a function that has a discontinuity, then what might happen is that as we approach from one side, we're approaching some maximum value, but if we have a discontinuity, then the actual value there would be smaller. So you can get closer and closer and closer and closer to this maximum value here, but this maximum value is not achieved. And in this case, this function actually has no maximum value because this value is not achieved. And any lower value can be surpassed by just getting a little bit closer, a little bit closer. So if we have a function like this, the range of this function would actually be a half open interval. This might be from 0 to 2, for example. You might be able to get closer and closer and closer to this y value 2, but never achieve it. And so the range would be a half open interval. And so it would not achieve its maximum value. And the conclusion of the extreme value theorem would not apply in this case because the function is discontinuous. So this illustrates that the function really does need to be continuous. Let's look at one more example where the function is defined on a closed interval, and it's continuous where it's defined, but there's a point where, well, it's defined on most of a closed interval, but not the whole thing. So here, again, this function violates the hypotheses and fails at having a maximum value. Let's look at one last case where this happens. So if we look at a function like, I don't know, f of x equals x minus 1 quantity squared, and let's negate it. So we would have something like this. If you plug in 0, you get minus 1. Plug in 1, you get 0. And then plug in 2, then you'd get -1 again. So this is a parabola here, opening downwards. Now this has a maximum value here, but if we change this function so that it's a piecewise definition, so f of x equals this if x is not equal to 1, and undefined if x equals 1. So this is a little bit strange thing to do, but we could just create a hole here. So the function is continuous where defined, but now it has this hole in the graph. Then because we've removed this, which was the maximum value, then it has no maximum value. And then like the previous example, we can get closer and closer and closer to 0, but we can't actually make it equal to 0. So this might seem like a fairly contrived example, but another way of expressing this function is we could have negative x minus 1 cubed over x minus 1, something like this. And then this function would be truly undefined when x equals 1 because we've got 0 in the denominator. So this might be an alternate form that would justify having a 0, having a place where the function is undefined. So if we have this function, if we cancel these, we get a different function, and then it is continuous. But if we don't cancel them, then this function is undefined at x equals 1, and so it doesn't take its maximum value. So this is just to say that all the hypotheses of this theorem are really important, that the function really does need to be defined on a closed interval and all of that closed interval, and it really does need to be continuous on that closed interval. And then under those conditions, we do expect that there will be a maximum value on that interval. And we can find it using calculus if the function is differentiable. But that's kind of not the point of this theorem. Okay, so how do we prove that there is a maximum value? What we're going to do here is we're going to use a two-step process. We're going to consider the range of this function, and we're going to try to prove that the range of this function has a maximum value, right? The global max is this value x naught, and then the output value here is going to be f of x naught. So if we look at the range of this function in my sketched example here, the range in purple would be this interval. So what we really need to do to identify the maximum is to find this upper limit of the range. So what we're going to do in this proof is we're going to focus our attention on the discovery of the highest point in the range of this function. Now that's really two questions. There are two concerns that we should have if we're looking for the highest point in the range. The first concern that we should have is the range even bounded? So if it's not bounded, then we can't find that highest point. So the first concern is that range even bounded at all? We'll have to deal with that. Then once we know that it's bounded, we're still not done. When it's bounded, we take the supremum of the range, but we don't know necessarily. I mean, it could be bounded, but have a hole here, right? So it could be bounded, but not achieve that maximum. Then when we look to the supremum of that, we need to say, okay, that supremum is actually a maximum. It's in the range. It is f of x naught for some x naught, not just, you know, some hole there. So those are our two concerns. We need to first prove that the range is bounded, and then we need to prove that the supremum of the range is in the range and is therefore a maximum value of the range of the function. And then we will know that there must be some x naught, so the f of x naught is actually equal to that key value. So that's going to be the strategy. Now, to tell the truth here, both of these concerns are related, and you'll see that the proof kind of is parallel in these two different concerns, right? Proving that it's bounded, and then we're going to do a trick, and then proving that that bound is actually achieved. We're going to kind of do the same trick. And to tell the truth, both of these parts can be handled in one go with a very clever finesse, transforming the function a little bit. But the finesse is harder than doing the trick twice. So instead of being tricky, we're just going to apply the same strategy of thinking twice. You probably, it will probably be easier to follow that way. So, so let's get to the proof here. So proof. Our first claim is that the range or image, let's say image because it's less ambiguous. So the image, which is the set of all f of x, so where x is in AB, the image is bounded. So we want to show that it's bounded. And then actually, because we're dealing with a maximum, we really only need to assert that it's bounded above. So our first step is going to be to claim and prove that this image of the function is bounded. Basically, this is what I've represented in purple here. It doesn't go up to infinity. And in order to prove this claim, we're actually going to use a proof by contradiction. We're going to suppose that this range is unbounded. So suppose it's unbounded. So we have an unbounded range. And then that means that no matter how high you get along the y-axis, there is some x value such that f of x exceeds that. So let's state this. So then for any n, and I want you to think of that as like an integer value along the y-axis, but higher and higher and higher. So then for any n, there exists an x in the domain of this function so that f of x actually exceeds n. That's a way of expressing that this thing is unbounded, right? If it's unbounded, then any integer you pick, you can get even higher than that. So this is what it means for it to be unbounded. We're supposing this for contradiction because I want to show that it's bounded. So I'm going to use this and I'm going to try to get a contradiction out of this. All right, what do we get from this? We can actually make a sequence of values. So this is why I chose a little n instead of, for example, a cap m to express this unboundedness. So for every n, there is some x in the domain, and then f of x is going to exceed that little n. So what I'm going to do is I'm going to pick a sequence of these values. So I'm going to choose, so let me say for each n. So for each n, I'm going to choose an x sub n in this thing so that f of x sub n exceeds n. So basically, I'm going to choose, let's get rid of x naught here. I'm going to choose x1 so that the value here exceeds 1. And then I'm going to choose x2 so that the value here exceeds 2. And then if 3 is here, I'm going to choose x3 so that the value there exceeds 3. And then I might have to look somewhere else to find a value x4 whose value f of x4 exceeds 4. So maybe 4 is here, and maybe this is f of x4. So I'm going to just bounce around within the interval a, b, choosing these values xn, which are greater than n. I know that this is possible because I've assumed that the thing is bounded on this, that is unbounded on this interval a, b. All right. Now we have a sequence of values. So this yields a sequence. A sequence xn. And now that we have a sequence, now we should start talking about convergence and divergence. But this actually doesn't just yield one sequence, it yields two sequences. It yields the sequence of values x1, x2, x3, x4, but it also yields the sequence of f of x values, f of x1, f of x2, f of x3, f of x4. So this yields a sequence xn and another, which is the sequence of y values associated with them, f of xn. So what are we going to do with these sequences? Well, actually, you might think that the xn is easier to deal with because it's the x values, but the sequence of the y values is much easier to deal with because these exceed n. And so since the sequence n, just n itself, diverges to infinity, and since f of xn is greater than n for all n, we can conclude that the sequence f of xn also diverges to infinity. So this is by the comparison test for diverging to infinity, right? If you have a sequence an and a sequence bn, bn is bigger, an already converges to infinity, then bn has to converge to infinity as well. So so here, this sequence 1, 2, 3, 4, 5, that diverges to infinity, and then and then this is bigger, so it also diverges to infinity. So that tells us that f of xn diverges to infinity. Okay, so that's interesting. We get these values diverging to infinity. That's not surprising because we assumed that it was unbounded. What does the sequence xn do? Well, honestly, like, who knows? It could do anything. Xn is just chosen within this interval AB. I'd like to talk about the limit of the sequence xn. That would be interesting, but I really can't. Because the sequence xn is just like pick any value so that f of x is bigger than that. I don't really know what the behavior of the function f is. I don't know where it's greater than 5, where it's greater than 6, where it's greater than 7, if there's some, some pattern. So I don't know how the xn's will be chosen within this interval AB. I know basically one thing about the sequence xn, and that is that it's bounded. It's bounded below by A, and it's bounded above by B. But I don't, so I can record that, but I don't know what the limit is. So notice xn is bounded. That's the only thing I really know about it. It may be jumping around. Maybe x1 is here, x2 is here, x3 is 4, x5, x6, x7, x8. I don't know. It could be jumping around. It could just cover lots and lots of values here. We don't have a reason to believe that that sequence converges to anything. And that means that's really bad news, because that means that we can't talk about the limit of that sequence. But it is at least bounded. And now we get to use some of the earlier tricks that we've used, especially when we were dealing with Cauchy sequences. If only it were a bounded monotone sequence. And you might think, oh, it's monotone increasing because we chose it to be. Well, no, it's not necessarily. I mean, the fxn's are getting larger and larger and larger, but the xn's themselves, well, even that is not necessarily true. Like, 1 is greater than 5, the next is greater than 6. If it's working ahead and it's already greater than 10, who knows what could happen. So the fxn's at least look like they're an increasing sequence, although there's no actual guarantee of that in this proof. The xn's themselves are not necessarily increasing, and they're not necessarily decreasing. So we don't know. But when we proved this stuff about Cauchy sequences, one of the things we proved was that any sequence at all has a monotone subsequence. And so we can choose from the xn's a monotone subsequence. Well, big deal. Okay, so let's choose it. And I'm going to give it a different letter. So let's let Tn be a monotone subsequence of xn. So it's some of the xn's, but not all of them. And I'm calling it T, but it still is like from A to B. It's still moving around. So I don't know whether it's an increasing subsequence or a decreasing subsequence, and I don't care. It's monotone. So this is one of the things we proved when we were dealing with Cauchy sequences. Any sequence has a monotone subsequence. So what? So it's monotone and it's bounded. So what? Whoa, wait, there's a theorem about that, right? If you have a monotone bounded sequence, and xn's are not, but the tn's are, so the tn's are a monotone bounded subsequence. Any monotone bounded subsequence converges to something. And so now we can start talking about the limits. So, so then let's state this. Tn is bounded and monotone. And by the bounded monotone convergence theorem, it converges. So Tn converges. And then we can say the limit of the Tn's is equal to something. And I'd like to say it's equal to x naught and declare victory here, but let's not jump the gun. Let's just say it's equal to t, right? We've got Tn's, we got to choose something they converge to. Let's just say it's equal to t. So it equals, this is by the monotone bounded convergence theorem, that must have a limit. Okay, now something interesting happens. Now that the Tn's have a limit, then we can think about that limit in the context of the function f. Now, f is a continuous function. And as a continuous function, it obeys both the epsilon delta definition of continuity and the sequential definition of continuity, which says, as long as you have any sequence of values in the domain converging to some limit, then the sequence of f of those values will converge to f of that limit. Applying that to this situation gives us something interesting. So then the limit as n goes to infinity of f of tn is equal to f of t. Now, if you're worrying about whether f of t exists, f of t does necessarily exist. It's the limit of tn. The tn's must converge to some value within the closed interval ab, and f is defined on the entire closed interval ab. So f of t definitely exists here, and this tells us that the limit of f of tn is equal to that value f of t. So this is some finite value. I don't know what it is. I have no idea. But this, what is that? We already know that the sequence of f of xn's diverges to infinity, and this is just a subsequence of it. So this thing has to diverge to infinity. So this diverges to infinity. And now we have our contradiction. So I should state this comes from continuity, right? So maybe to clarify here, let's not just say by sequential continuity is how we got that of f. That's how that equation came to be. We have this limit, we apply f to both sides, and therefore this limit must also be true. That's the sequential continuity of f. But what it gives us is this is a finite value, and this limit has to be infinite because it's a subsequence of something that we specifically chose to diverge to infinity. So this one is going to be infinite. This one is finite. They're equal. That's no good. That doesn't make any sense. And so this gives us our contradiction, which I'm just going to indicate this way. That's a contradiction. So what does this contradiction mean? What has happened here? We supposed for contradiction that this thing was unbounded, and we ended up in this contradiction. So what it means is, I guess it's bounded. So we conclude, the right conclusion here is that the set of all f of x, so that x is in the not the reals, so that x is in the domain AB is a bounded set. Now, that's half of what we need. So basically that says that what I've represented happening in purple here is essentially correct. This set does not go on forever up to infinity. The next worry that we have to have is that this set is bounded but does not achieve its supremum value. Something goes wrong. You can get closer and closer and closer to this supremum value, but you can't achieve it. So the next thing we need to deal with is this possibility. And we're going to use a similar proof to this one to demonstrate that you can actually achieve that. So that's going to be in part 2 of this proof. And we'll get to that in the second half of this video.